Welcome to the deep dive. This is where we really get into the technical manuals, the research, pulling out the practical knowledge you need, not just for exams, but for safety, for doing the job right.
Well, exactly.
Today, we're tackling a really critical area of aviation electricity, the fundamentals of AC power and its regulation. This stuff is, well, it's the heart of modern aircraft systems.
It really is. And if you're an AMT General Course student, think Chapter 12, Part 4.
Yeah.
This is your guide to understanding, everything from those specialized AC motors through to the complex ways we keep power constant and reliable.
So what's the mission for today?
Our mission basically is to cut through some of the density in the source material. We'll dissect the synchronous motor, the AC series motor, look at how these high power alternators are designed, how they're connected, Y versus delta. And then, crucially, we'll get into the control systems, constant speed drives, the GCUs, transistorized regulation, all that good stuff.
And the context here is really foundational, isn't it? This material helps bridge the gap, moving from simpler DC systems, maybe on smaller aircraft, to what's needed for turbine aviation.
Absolutely.
Huh.
It's the difference between, say, wiring up a nav light on a piston single versus troubleshooting a generator that has to put out exactly 400 cycles per second on a big jet.
Constant speed, constant voltage, perfect frequency. That's the goal.
That's the game. And we're going to explore exactly how the aircraft pulls that off. So let's maybe start with those specialized motors, the AC ones that sometimes need a bit of a kickstart.
Okay, kicking things off with the synchronous motor. Now, when people hear AC motor, they usually jump straight to the induction motor. But this one's different.
It operates on a very distinct principle, yeah. The key thing here is its torque doesn't come from induced currents in the rotor, like an induction motor. It's about two separate magnetic fields interacting directly.
Okay, walk us through that operation then, because the precision aspect seems really important here.
Right. So it starts with the stator, the stationary part. You feed multi-phase AC into the stator windings.
Okay.
That creates a magnetic field that rotates rapidly. That rotating field sets the speed. Now, the rotor is different. You supply it with DC current.
DC, okay.
Yeah, usually through windings and slip rings, though sometimes it might be a permanent magnet on simpler ones. This DC creates a second distinct magnetic field on the rotor.
So you've got this rotating magnetic field from the stator and then a magnetic rotor sitting inside it. What happens?
The two fields lock together magnetically. The rotor's field latches onto the stator's rotating field and it gets dragged along at the exact same speed. Perfectly synchronized.
Hence the name, synchronous.
Exactly. Which makes it perfect for things that need absolute speed stability. Think precision timing devices, maybe certain instruments.
But that perfect synchronization, while great for stability, that's also its main weakness when you put a load on it, right?
Oh, absolutely. It's very sensitive to overload. If the load on the shaft is too heavy, the rotor just can't maintain that magnetic lock. It starts to slip, pulls out of sync with the rotating field.
It falls behind.
And basically stops working correctly, which, immediately tells the technician, hey, this motor, or whatever it's driving, is seriously overloaded.
Now, the source material mentions a sort of basic concept where the stator induces poles in a soft iron rotor, but it says that's impractical. Why?
Yeah, that's more of a theoretical starting point. In reality, those induced poles would be far too weak to handle any real mechanical load. For anything practical, especially in aviation, you need strong, controllable fields.
So that means?
That means using DC-energized rotor windings, fed through slip rings. And this is where some control comes in. You usually put a rheostat in series with that DC supply.
Ah, the rheostat. And what does that let the technician control?
It lets you vary the strength of the rotor poles by adjusting the DC excitation current. This is pretty vital for managing how the motor performs under different loads, helping it stay locked in sync right up until that overload point.
Okay, this brings us to the synchronous motor's, let's say, most famous quirk. It's not self-starting.
Yup, not at all. If you just hit it with AC on the stator and DC on the rotor while it's sitting still, nothing useful happens.
Oh, why not?
The rotor's just too heavy, its inertia's too great. That rotating field from the stator whips past the stationary rotor poles so fast, the magnetic lock just can't grab on. The rotor might wiggle a bit, but it won't start turning.
So you need to give it a push first.
Essentially, yes.
Yeah.
You need to get it up to near its operating speed before you energize that main DC field.
How do engineers solve that? What are the design strategies?
Well, there are a couple of main ways. One, maybe less common now, is using a small auxiliary motor like a little AC or DC pony motor.
Right.
That spins the main rotor up to maybe 90% of synchronous speed. Once it's cruising close to speed, then you apply the main DC field power and wham, it locks in step.
Okay. And the other method? the one that's more common.
That involves building a sort of temporary induction motor right onto the rotor itself. You add a squirrel cage type winding to the rotor structure.
Ah, clever.
Yeah. So when you first apply AC, this squirrel cage winding acts just like a standard induction motor. It provides the starting torque to get the rotor spinning almost up to synchronous speed.
Okay.
Once it's close, maybe 95% speed, you apply the DC excitation. The main field takes over, locks the rotor in sync, and that squirrel cage winding just goes along for the ride, effectively doing nothing during normal operation.
That's a neat solution. Solves the starting problem without needing a whole separate motor. Okay, let's switch gears now to the AC series motor, the universal motor.
Right, the universal workhorse. It's an interesting one because structurally, it looks almost exactly like a DC series motor. You've got brushes, you've got a commutator.
And the series part means the armature and field are wired in series.
Correct. And because of that series connection, it has the unique ability to run on either AC or DC power, hence universal.
But in the material, you can't just grab any old DC series motor, plug it into an AC outlet, and expect it to work properly. It'll likely fail pretty quickly.
Oh, spectacularly. Yeah. You absolutely need to understand why it fails on AC before you can appreciate the design fixes. Basically, 3 big problems.
Okay, problem number 1.
Excessive heat and really poor efficiency. DC motors often have solid iron field frames and poles because the magnetic flux isn't changing. But when you apply AC, that rapidly alternating flux induces huge eddy currents within the solid iron.
Like little swirling currents causing heat.
Exactly. Massive heat buildup. Plus, you get hysteresis losses, energy wasted, just flipping the magnetic polarity back and forth in the iron. So, first issue. It gets dangerously hot and wastes power.
Got it. Heat. What's issue 2?
Low power factor. The alternating current creates a lot of self-induction or reactance in both the field and armature windings. This high reactance throws the voltage and current significantly out of phase.
Which means
the motor draws way more current from the line than it needs for the actual mechanical work it's doing. It's electrically inefficient.
Okay, heat, poor power factor. And the third issue sounds like it involves a commutator.
It does. That's the excessive sparking. The alternating magnetic field induces large currents in the armature coils that are momentarily short-circuited by the brushes as they pass over the commutator segments.
Ah, sparks fly.
Big time. Severe, destructive sparking that quickly pits and burns the commutator and brushes. It just chews them up.
So to make a series motor that actually works well on AC, engineers had to make some significant design changes to tackle these 3 issues. Let's break down the fixes. First, dealing with the heat.
Right. To kill those eddy currents, the entire magnetic path field poles, the frame, the armature core, has to be laminated, built up from thin sheets of metal insulated from each other. And to minimize the hysteresis losses, those laminations need to be made of a special material. High permeability, silicon steel, much like you'd find in a transformer core.
So laminations handle the heat. What about the low power factor and high reactance?
You have to attack reactance in both the field and the armature. For the field, designers use things like shallow pole pieces, fewer turns of wire, lower magnetic flux density, and a really short air gap between the pole and the armature. Historically, for very large AC series motors, they sometimes even use lower frequencies like 25 Hz. But that's not relevant for our standard 400 Hz aircraft systems.
And for the armature reactance, there's a special winding involved.
Yes, the compensating winding. This is crucial. It's embedded in the pole faces and is designed to create a magnetic field that directly opposes the armature's magnetic field.
It cancels it out.
Pretty much. It neutralizes the armature reaction, which significantly improves the power factor and the motor's overall efficiency.
The material mentions 2 ways this winding can be connected, conductively or inductively. What's the difference there?
If it's wired directly in series with the armature, that's conductively compensated. The same current flows through both, ensuring the opposing fields match up well. If it acts more like a transformer primary, inducing a current in a shorted winding to cancel the flux, that's inductively compensated. For motors really designed to run well on both AC and DC, the conductive series connection is usually preferred.
Okay, that handles reactance. Finally, how do they stop that terrible sparking at the commutator?
They use what are called preventive leads. These are basically leads with a relatively high resistance connected across the armature coils that get shorted by the brushes.
How's that held?
The resistance limits how much current can flow through that shorted coil when it's passing under the brush, which drastically reduces the energy available to make a spark. Designers also use things like single-turn armature coils and multiple poles to keep the voltage between adjacent commutator bars low, usually under 250 volts or so.
And those smaller universal motors, like in a drill or a fan?
Right, those fractional horsepower ones often skip the compensating windings, and maybe even the preventive leads. They can get away with it because the currents and voltages are much lower and the performance demands aren't as critical.
It really highlights how much extra engineering goes into making something work reliably with AC compared to DC. Okay, we've covered these specialized motors. Let's move on to where the AC power actually comes from, the alternator.
Right, the alternator or AC generator, its job is straightforward. Convert mechanical energy from the engine into AC electrical energy. The fundamental principle is still electromagnetic induction, just like a DC generator.
But the key difference for a technician lies in how the output is collected, right?
Exactly. The alternator uses slip rings to connect the generated AC to the external circuit. A DC generator uses that segmented commutator, which acts as a mechanical rectifier, switching the connections to produce DC.
Okay. Now, alternators get classified in a few ways. First up is how they get the DC needed for their magnetic field. How is that field excited?
There are three main methods described. The sort of traditional way is using a direct connected DC generator. Often a small DC generator, called an exciter, is mounted right on the same shaft as the alternator.
So it makes its own DC.
Makes its own DC to feed its own field. Or sometimes you might use battery power initially to flash the field and get things started, and then it becomes self-exciting.
Method 2.
Transformation and rectification. This relies on a tiny bit of residual magnetism left in the iron core. When the alternator starts spinning, this generates a very small AC voltage.
Just enough to.
Just enough to be immediately rectified, turned into DC, and fed back to the field winding. This boosts the field, which generates more AC, which makes more DC, and the voltage rapidly builds up on its own.
And the third method, the one we see on bigger modern aircraft.
That's the integrated brushless type. This is really the standard for high-power applications because it gets rid of high-maintenance parts. It still uses a DC exciter generator on the shaft, but here's the clever part. The AC output from the exciter's rotating armature is rectified by silicon rectifiers that are mounted right on the rotating shaft itself.
So the AC gets turned into DC while it's still spinning.
Precisely.
Yeah.
And that DC is then fed directly into the main alternator's rotating field winding, which is also on the same shaft. No need for brushes or slip rings to handle the main field current.
That sounds much more reliable.
Way more reliable. Eliminates a major wear item.
Okay, now construction-wise, the material says one type is almost universally used in aircraft. Which one and why?
It's the revolving field type. That means the armature windings where the main power is generated are a stationary part of the stator. The magnetic field system, the rotor, is the part that spins.
And the advantage of having the high-power winding stationary.
It's a huge safety and maintenance advantage. The high current going out to the aircraft systems comes directly off these stationary stator windings. You don't need to transfer potentially thousands of amps through sliding contacts like brushes and slip rings.
Which would be a nightmare.
Oh, a total nightmare. High voltage, high current slip rings wear out fast, they arc, they're hazardous. By using a revolving field, the only thing the slip rings, if used like in non-brushless designs, need to handle is the relatively low voltage, low current DC for the rotating field. Much easier, much safer, much more reliable.
Makes perfect sense. So we have revolving field alternators. The next classification is by phase. Single, two, three-phase.
Right. While single and two-phase exist, virtually all significant aircraft power generation is three-phase.
Briefly, what are the other two?
Okay, single phase is the simplest. All the windings are basically connected in series, so their voltages add up. Think basic household AC. Two-phase uses two sets of windings physically offset by 90 degrees in the stator. This gives you two AC voltages that are 90 degrees out of phase with each other. Not very common anymore.
And the standard three-phase.
Here you have three separate single-phase windings spaced evenly, 120 degrees apart, around the stator. This produces three distinct AC voltages, each 120 degrees out of phase with the others.
Why is three-phase so dominant?
It provides much smoother, more constant power delivery compared to single or two-phase. For driving motors, it gives more uniform torque. For power transmission, it's more efficient. This is better suited for the high-density, stable power needed in aviation.
Okay, so we've got three-phase power. But how you connect those three windings together, Y or delta, makes a big difference in the output. This seems like a really fundamental concept for understanding the power bus architecture.
Absolutely critical. Let's start with the Y connection, sometimes called the star connection. Picture the three windings. You take one end from each winding and connect them all together at a common point.
Like the center of a Y shape.
Exactly.
Yeah.
And that common point is often brought out as the neutral lead. Now, for the AMT student, the key thing is what this connection does to voltage and current, assuming the loads are balanced.
What does Y prioritize?
Y gives you a voltage boost. The voltage measured between any two of the three main lines, the line voltage, is higher than the voltage generated in any single winding, the phase voltage. Specifically, the line voltage is the square root of 3, or about 1.73 times the phase voltage.
But the current?
The line current is the same as the phase current in a Y connection, so you trade current capacity for higher voltage.
Why would it want that higher voltage?
It's more efficient for transmitting power over distances, like down the length of a large aircraft bus. Higher voltage means lower current for the same amount of power, which means less loss in the wires. I2 losses.
Okay, that's why. Now, the alternative is the delta connection. How's that set up?
In delta, you connect the windings end to end, forming a closed triangle shape, like the Greek letter delta.
And how does that change the voltage and current relationship?
It flips the Y situation. In a delta connection, the line voltage is equal to the phase voltage. No voltage boost here.
But the current?
The line current is 1.73 times the phase current. So delta gives you a current boost at the expense of voltage multiplication.
So if Y gives you voltage, delta gives you current, why choose delta?
Well, sometimes you need to deliver a lot of current to a specific load nearby. Also, delta has a bit of inherent redundancy. If one winding fails in a delta system, the other two can sometimes continue to supply power, although at a reduced capacity. It can keep things limping along.
Are both used in aircraft?
You'll see both, depending on the specific application and design philosophy.
Okay.
But for the main power distribution buses on larger aircraft, Y is often preferred because of that voltage step up and the availability of a neutral reference point.
Okay, Y versus delta. Crucial distinction. Now let's talk frequency. Arguably the most critical parameter for AC systems on aircraft. That magic number. 400 hertz or 400 cycles per second.
Absolutely critical.
Right.
And the output frequency of an alternator depends on only two things: the number of magnetic poles built into it and how fast the rotor is spinning.
There's a formula for this.
Very fundamental one.
Mm-hmm.
Frequency F equals the number of poles, P times the speed in RPM in, all divided by 120. So $5, P times N, 121.
Let's plug in some typical numbers. Say a 12-pole alternator needs to produce 400 hertz. What speed does N need to be?
Okay, 412 in Med 120, rearranging that, N 100 and 120, 12, which comes out to exactly 4,000 RPM.
So to get 400 hertz from a 12-pole alternator, it must spin at 4,000 RPM.
Precisely. Now, if you had a simpler two-pole alternator, like you might find in ground power systems generating 60 hertz, you'd need N in place at 60, 122 equals 3,600 RPM.
Here's the problem, though. The engine driving this alternator doesn't spin at a constant speed. It varies hugely.
Exactly. From idle on the ground to take off power, the engine RPM, and thus the input speed of the alternator drive, changes dramatically. If N changes, the formula tells us F changes.
And almost everything on the plane using AC power demands that constant 400 hertz. Motors, electronics, instruments.
Right. They're designed for it. So we have a major engineering challenge. How do you keep N, the alternator speed, absolutely constant when the input speed from the engine is all over the place?
That sounds like the job for the constant speed drive we mentioned earlier.
That's exactly what the CSD does. We'll get into the details of how it does that later. But its sole purpose is to ensure the alternator spins at the precise speed needed for 400 hertz, regardless of engine RPM.
Before we get to the CSD, how are alternators rated? It's not just watts like DC generators.
No, AC generators are typically rated in kVA kilovolt amperes. That's a measure of apparent power. The rating plate will also list the power factor it's designed for, the number of phases, the output voltage, and of course, the frequency.
Why kVA instead of kW, kilowatts?
Because the limiting factor for an alternator is usually heat generated by current flowing through its windings, those I2 vertical line losses. kVA represents the total voltage and current the alternator can handle, regardless of the power factor of the load. Kilowatts only represent the real power doing useful work.
So kVA is about the thermal limit.
Largely, yes. It tells you the maximum current the windings can carry without overheating.
Wow.
And something for technicians to remember, Loads with a poor lagging power factor actually tend to weaken the alternator's magnetic field,
Meaning?
meaning the voltage regulator has to work harder, increasing the DC field current just to keep the output voltage stable. It puts more stress on the excitation system.
Good point. Okay, let's quickly touch on a couple of integrated units that use these principles. First, the alternator rectifier unit, or ARU, common on smaller planes.
Yeah, typically found on aircraft under 12,500 pounds that primarily use DC power. An ARU is basically a small alternator, often self-excited, maybe delta-connected, whose AC output immediately feeds into a built-in three-phase full-wave bridge rectifier.
So it makes AC but instantly converts it.
Exactly. Usually uses 6 diodes to turn the three-phase AC into DC, typically putting out around 26 to 29 volt DC for the aircraft's systems. It's a simple way to get DC power from a lightweight rotating machine.
And for the big power demands on larger aircraft, we have the brushless alternator. We touched on it, but let's revisit the internals.
Right, this is the high-power, low-maintenance standard now. It's really like 3 rotating machines on one shaft. You have a small permanent magnet generator acting as a pilot exciter. Its output powers the field of a slightly larger AC exciter generator.
Okay.
Now, the AC output from the rotating armature of this exciter generator is fed into that set of rectifiers mounted inside the rotating shaft.
The ones that spin with it.
Yes, they convert the exciter's AC to DC right there on the shaft, and that DC is then fed directly into the winding of the main alternator's rotating field.
Completely eliminating brushes for the main field current.
Totally gone. Huge reliability improvement. And because it starts with a permanent magnet pilot exciter, it usually doesn't need external field flashing to get started. It builds up voltage on its own.
Very efficient. And one more integrated unit, the starter generator.
Another clever weight-saving design, especially prominent now on aircraft like the 787, but the concept's been around. It does double duty.
How so?
For engine start, it functions as a powerful DC motor, using battery or ground power to crank the engine over. Once the engine lights off and reaches self-sustaining speed, control circuits automatically reconfigure its connections, and it switches modes to operate as a generator, supplying power back to the aircraft buses.
One unit does both jobs.
Saves the weight and space of having a separate starter motor and a separate main generator. Very common on turbine engines now.
Okay, we've generated the AC power, now we need to control it. We know the frequency is handled by keeping the speed constant, but the voltage also needs to be stable.
Absolutely. Engine speed changes, load changes. These things would cause the output voltage to fluctuate wildly if we didn't regulate it. And we established earlier, the easiest, most effective way to control the output voltage is by adjusting the strength of the magnetic field.
By controlling the DC current going to the field winding?
Exactly. That field current is the control knob. Whether it's an old-school mechanical system or a modern digital one, they all ultimately work by tweaking that field current.
Let's look at the evolution of regulators. Starting with the older mechanical vibrating type regulator, how did that work?
It's actually quite ingenious, using basic electromagnetism. It has a voltage sensing coil, basically a solenoid, connected across the generator's output terminals.
Okay.
As the generator voltage rises, the magnetic pull of this solenoid gets stronger. At a specific voltage point, the pull becomes strong enough to overcome a calibrated spring and physically pull open a set of electrical contacts.
And opening those contacts does what?
Opening the contacts inserts a resistor, the field rheostat, into the field winding circuit. This added resistance immediately reduces the DC field current.
Less field current means less magnetic field, which means less output voltage.
Correct. So the voltage starts to drop. As it drops, the solenoid weakens, the spring pulls the contacts closed again, shorting out the resistor, field current jumps back up, voltage starts to rise.
And the cycle repeats. It's constantly opening and closing, vibrating.
Exactly. Rapidly vibrating, trying to maintain an average voltage level. But this rapid cycling causes a couple of problems that need solutions.
Like what?
Well, first, all that mechanical buzzing isn't ideal. So they added a dashpot, a small air or oil-filled cylinder with a piston to dampen the movement of the contact arm, smoothing things out. Think of it like a tiny shock absorber.
Okay, smooths the vibration. What else?
Every time those contacts open while carrying current to an inductive load, the field coil, you get an electrical arc, a spark. This burns and pits the contacts over time.
So you need spark suppression.
Right. They put a capacitor across the contacts. The capacitor absorbs the energy spike that would cause the arc, protecting the contact surfaces.
Seems clever, but also sounds like it has limitations.
The big one is current handling. If the alternator needs a really large field current, those vibrating contacts just can't handle switching it on and off constantly. They'd burn up very quickly. So these were limited to smaller generators.
Which led to more complex mechanical systems for larger DC generators, like the 3-unit regulators found on many older light aircraft. What did those combine?
They typically packaged 3 distinct regulators into one housing. The voltage regulator, which works similarly to the vibrating type we just discussed, but added a current limiter and a reverse current cutout.
Okay, what did the current limiter do?
This protected the generator itself from overload. Unlike the voltage regulator coil, which sensed voltage, the current limiter had a heavy winding connected in series with the main generator output line.
So it measured the actual current flowing out.
Exactly. If the current being drawn by the aircraft exceeded the generator's maximum safe rating, the magnetic pull of this series coil would overcome its spring and open a set of contacts.
Inserting resistance into the field circuit again.
Yes, inserting another resistor into the field circuit, which forced the generator voltage down. Lower voltage means lower current output. It protected the generator from burnout due to excessive load, acting purely based on line current, not voltage.
And the 3rd unit, the reverse current cutout. Sounds important.
Absolutely essential for battery-equipped systems. Its job is to prevent the battery from discharging back into the generator if the generator's voltage drops below the battery's voltage.
Which would happen if the engine slows down too much.
Right, like during engine shutdown or if the generator fails. If the generator voltage falls below battery voltage, current will try to flow backwards from the battery to the generator, essentially trying to run the generator like a motor.
How did the cutout stop that?
It used 2 coils on one core. A fine wire voltage coil connected across the generator output, trying to close the main contactor relay, and a heavy wire current coil in series with the output line. Normally, current flows out, and both coils' magnetic fields add together to hold the relay closed.
But if current flows backwards?
If current reverses, the magnetic field from the series coil opposes the field from the voltage coil. This weakens the total magnetism enough for a spring to snap the main contacts open, instantly disconnecting the generator from the battery bus.
Protecting the battery and preventing the generator from being motored.
Exactly.
Okay, for larger aircraft, especially with AC systems, the connection and disconnection needs to be even more precise. That brings us to the differential relay switch.
Right. This serves a similar purpose to the reverse current cutout, but adds more precision and often functions as the main relay connecting the generator to the bus. It ensures the generator is only connected when its voltage is slightly higher than the bus voltage.
How much higher?
Usually a very specific small tolerance, maybe 0.35 to 0.65 volts higher. This prevents connection if the voltages aren't properly matched. It uses a combination of voltage sensing relays and differential relays that compare generator and bus voltages very accurately.
And it still provides reverse current protection.
Oh, yes. If it senses even a small, nominal reverse current trying to flow back into the generator, the differential relay trips, disconnecting the generator much faster and more reliably than the older mechanical cutouts.
Now we jump to the modern era. Solid state, microprocessors, the generator control unit, or GCU. This sounds like the brain of the operation.
It absolutely is on most turbine aircraft. The GCU takes all those functions we just discussed, voltage regulation, connection control, protection, and integrates them into one, usually digital, box.
So its main job is still voltage regulation?
Primary job, yes. It constantly senses the generator's output voltage, compares it to a very precise internal reference voltage, and calculates the exact adjustment needed for the field excitation current to keep the voltage perfectly stable.
But it does a lot more than just regulate voltage. What are the key protection features an AMT needs to understand?
There are several critical layers. Overvoltage protection is a big one. If the regulator itself fails and the voltage starts to run away, the GCU will detect this and immediately open the circuit, providing power to the field, shutting the generator down to protect sensitive avionics.
What else?
In systems with multiple generators running in parallel, over-excitation protection, sometimes called field weakening, is vital. If one generator, maybe due to a fault, tries to carry way more than its fair share of the load, gets overexcited, the GCU can detect this imbalance and reduce that generator's field current, forcing it to share the load properly or even take it offline if necessary.
It also handles the connection logic.
Yes, using differential voltage sensing, just like the relay switch, it ensures the generator's voltage and frequency are perfectly matched to the bus before allowing the main generator control breaker, GCB, or generator line contactor, GLC, to close.
And parallel operation. How does it ensure generators share the load equally?
It constantly communicates, often via an equalizer bus or digital data lines. It compares its own generator's output parameters, voltage, current, load, with the bus conditions and the status of other online generators. Based on this, it makes tiny adjustments to its field excitation to ensure equal load sharing.
And reverse current.
Still crucial. It has highly sensitive reverse current sensing. If it detects current flowing back into the generator, it trips the main contactor instantly. The GCU really centralizes all the control and protection logic.
Okay, so the GCU is the brain. Let's peek inside the technology that makes this possible at high speed. The transistorized voltage regulator. This is where we get into solid-state components.
Right. These circuits are complex, using transistors, diodes, resistors, capacitors, often a Zener diode for a stable voltage reference, and maybe a thermistor to compensate for temperature changes. But we can break down the basic function.
How does it work? Stage 1.
Stage 1 is sensing and comparison. The AC output voltage from the alternator is typically rectified, using diodes, let's call them CR1, to get a DC voltage proportional to the AC output. This measured DC voltage is then compared to a very stable reference voltage, usually provided by that Zener diode, say CR5.
The Zener voltage doesn't change much.
Exactly. It provides a fixed benchmark. The difference between the measured voltage and the Zener reference voltage is the error signal. It tells the circuit if the generator voltage is too high, too low, or just right.
Okay, we have an error signal. Where does it go next? Stage 2.
Stage 2 is amplification. That small error signal is fed to the input, the base of a transistor, like Q1. Transistors act as amplifiers. A small change in the base current controls a much larger current flow through the transistor. This amplified signal might then be passed through several more transistors, maybe Q4, Q2, in sequence, each stage providing more gain.
So you end up with a much stronger signal representing the error. Stage 3.
Stage 3 is controlling the field. The highly amplified error signal is fed to the base of the main output transistor, say Q3. This transistor is connected in series with the alternator's exciter field winding.
So this transistor acts like an electronic valve for the field current.
Precisely. If the generator voltage was low, the amplified error signal increases the current flowing into Q3's base. This makes Q3 conduct much more heavily, allowing a large current to flow through it and out to the exciter field. More field current boosts the generator voltage back up. If the voltage was high, the opposite happens. Q3 conducts less, field current drops, voltage drops.
And this happens incredibly fast.
Extremely fast. Transistors can switch and adjust currents much faster than any mechanical relay, allowing for very precise and stable voltage regulation, even with rapid load changes.
Are there safety features built into these transistorized circuits too?
Usually, yes. You often find an underspeed switch function. This prevents the regulator from trying to apply field excitation if the alternator isn't spinning fast enough to generate power effectively. Trying to excite a stalled or slow-turning field is inefficient and could cause issues.
Makes sense. Anything else?
There's often a relay, maybe called K1 in the diagrams, that handles the initial field flashing. It momentarily connects the field to the aircraft's DC bus voltage when the system starts up, just to ensure there's enough magnetism to begin the voltage buildup process. Once the generator is producing its own power, this relay usually drops out.
Okay, we've covered generation and voltage regulation, but we keep coming back to that critical need for constant frequency, which means constant alternator speed, typically 6,000 RPM for 400 hertz.
And the engine driving it is anything but constant speed.
Right. Idling at maybe 2,800 RPM, takeoff power pushing 9,000 RPM or more. That huge speed difference is why we absolutely need the constant speed drive, the CSD.
The CSD is essentially a highly sophisticated, self-contained gearbox. But it's a hydraulic transmission, not just gears. It sits physically between the engine's accessory drive pad and the alternator.
And its only job?
Its one and only job is to take that widely varying input speed from the engine and produce a rock-solid, constant output speed for the alternator, ensuring that perfect 400 hertz frequency. Sometimes it's a separate unit, sometimes it's integrated with the generator into one housing, called an AMT-G integrated drive generator.
How does it manage to do that across such a wide input range? It must operate in different modes.
It does. It has three main operating modes, hydraulically speaking. If the engine input speed is lower than the target 6,000 RPM output, the CSD goes into overdrive. Its internal hydraulics work to increase the speed ratio, spinning the alternator faster than the input drive.
Okay, makes sense. What if the engine speed is close to the target?
If the input speed is right around 6,000 RPM, the CSD often goes into what's called straight drive, or sometimes hydraulic lock. The input and output speeds are essentially the same, and the hydraulics are doing minimal speed adjustment work. It's the most efficient mode.
And when the engine's really spooling up, like during takeoff or high-speed cruise, well above 6,000 RPM.
Then the CSD shifts into underdrive. The hydraulics now work to decrease the speed ratio, absorbing that excess RPM from the engine so the output to the alternator remains pegged at 6,000 RPM.
So it's constantly adjusting between overdrive, straight drive, and underdrive to maintain that output speed.
Continuously and automatically. This tight hydraulic control keeps the output frequency incredibly stable, typically only varying by a few cycles per second between no load and full load conditions, well within the required tolerances.
Let's get into the mechanics a bit. It's a hydraulic transmission using oil pressure.
Yes, it uses specialized hydraulic oil kept under pressure, often around 300 psi or more, by an internal charge pump. The core components involve two main rotating assemblies with pistons. There's a pump cylinder block, driven by the input shaft from the engine, and a motor cylinder block connected to the output shaft going to the alternator. Both blocks have multiple pistons.
And the magic is in how oil moves between them.
Exactly. The key control element is the angle of the pump wobbler plate, also called the swash plate. This plate pushes on the pump pistons. By changing the angle of this plate, you change how far the pistons stroke in and out.
More angle, more stroke, more oil pumped.
Precisely. A tilted pump wobbler forces oil under high pressure from the pump block over to the motor block. This high-pressure oil pushes against the pistons in the motor wobbler plate, forcing the motor block, and thus the output shaft, to rotate.
And the angle controls the speed ratio.
Yes. The angle of that pump wobbler plate, which is constantly adjusted by the governor system, determines how much oil is displaced per revolution. This controls the hydraulic power transfer and effectively sets the gear ratio between the input and output shafts, allowing it to maintain constant output speed.
It's like a continuously variable hydraulic transmission.
That's a great way to think about it. And there's an important safety feature built into the output drivetrain.
What's that?
There's usually an overriding clutch, often a Sprague-type clutch. If the CSD hydraulics were to fail, or if the alternator itself stopped generating and tried to draw power backwards, motoring, this clutch would instantly disengage the output shaft from the drive.
Preventing the alternator from trying to drive the engine backwards through the CSD?
Exactly. Protects the CSD and the engine accessory gearbox from reverse loads.
Okay, so what controls the angle of that critical pump wobbler plate? That's the job of the governor control system.
Right. It's typically an electrohydraulic system.
Yeah.
The primary speed sensor is a small tachometer generator driven directly by the CSD's output shaft.
So it measures the actual alternator speed?
Yes. It produces an AC voltage that's directly proportional to the output speed. This AC signal is usually rectified into DC and then fed into the control coil of the main valve and solenoid assembly.
How does that valve control the wobble plate angle?
That solenoid compares the signal from the attached generator, representing actual speed, against a reference, representing the desired 6,000 RPM. If the actual speed starts to increase, the attached generator voltage goes up, strengthening the solenoid's magnetic field.
Which moves the valve.
Moves the valve against a spring. The valve then directs hydraulic pressure to a small piston or cylinder that physically reduces the angle of the pump wobble plate. Less angle means less oil pumped, slowing the output speed back down towards 6,000 RPM. If the speed drops, the solenoid weakens, the spring moves the valve the other way, increasing the wobble plate angle to speed things up. It's a continuous feedback loop.
Very clever. Now, there are also dedicated circuits for safety and for operating multiple CSDs together. Let's start with overspeed protection.
Absolutely critical. If the main governor system fails and the CSD output speed starts to run away, potentially damaging the alternator, there's a backup. Usually, a mechanical centrifugal switch is set to close if the speed hits a predetermined limit, say 7,000 or 7,500 RPM.
What happens when that switch closes?
It energizes a dedicated overspeed solenoid. This solenoid forces the main control valve into a full, often latching underdrive position, regardless of what the main governor is trying to do. This slams the brakes on hydraulically, forcing the output speed down to a safe level.
A last line of defense against mechanical destruction.
Pretty much. And the other essential circuit, especially when you have two or more engine-driven generators operating in parallel, is the load division circuit, sometimes called a droop circuit.
Why is this needed for parallel operation?
You need the generators to share the total aircraft electrical load equally. If one generator starts taking significantly more load than the others, it could overheat and fail, potentially destabilizing the whole system. The load division circuit prevents this.
How does it measure the load?
It uses current transformers, CTs, installed on the output lines of each generator. These CTs measure the real load, the actual wattage being supplied by that specific generator.
Okay, it knows the load. How does it use that information to balance things?
The signal from the CTs, representing the real load, is typically fed to another control coil within the main governor valve assembly. This load control coil either aids or opposes the main speed control solenoid coil we discussed earlier.
How does aiding or opposing help balance the load?
Here's how it works. The generator that's carrying the highest real load will have a signal going to its load control coil that aids the main speed control solenoid. This makes the governor think the speed is slightly higher than it actually is, causing it to slightly reduce the CSD output speed for that generator.
Making it shed some load.
Exactly. Conversely, the generators carrying less load will have signals going to their load coils that oppose the main speed control solenoid. This makes their governors think the speed is slightly low, causing them to slightly increase their CSD output speed.
Making them pick up more load.
Right. These constant, tiny opposing adjustments between the CSDs force the real load to distribute evenly across all the operating generators. It ensures stable parallel operation.
Wow, that journey from understanding why a synchronous motor won't start on its own to the Y delta choices, the layers of voltage regulation, and finally this incredibly complex CSD balancing act. It really shows the level of engineering involved in aircraft power systems. Hashtag tag outro.
It really does. So let's try to wrap up the key practical points for you, the AMT student listening. We've seen how specialized motors like the AC series needed significant modifications, laminations, compensating windings just to handle AC power effectively. We saw the crucial difference between Y voltage boost and delta current boost connections for three-phase alternators. And the core principle of control, whether it's a simple vibrating relay or a sophisticated GCU, always comes back to managing that field current.
And the evolution in regulation itself is fascinating. From those early mechanical systems meeting physical damping with dash pots and spark suppression with capacitors, to the purely electronic, super-fast, multi-layered protection inside a GCU. It's not just regulating voltage anymore, it's managing parallel operations, protecting against overexcitation, sensing reverse current, all digitally.
And don't forget those sensory checks when you're working on the aircraft. If you hear a motor making overloaded grunting sounds, suspect excessive mechanical load. If a three-phase device is growling, you might have lost a phase. And always, always respect the heat. Use the back of your hand if it feels excessively hot, it's likely operating beyond safe limits. But ultimately, the manufacturer's maintenance manual is your final authority.
Absolutely.
The big shift we've really charted today is towards these highly integrated systems. The brushless alternator, the GCU, the AMT-G. This definitely minimizes some of the traditional hands-on tasks, changing brushes, cleaning commutators. That physical maintenance effort has largely been replaced by a need for advanced troubleshooting skills, understanding fault codes, interpreting data, and really grasping the complex logic within these solid-state systems.
So, a final thought for you to ponder as you continue your training. How does the shift from physical components to complex software and solid-state control change the game for the AMT? How do you translate your understanding of these fundamental electrical principles, vector sums in Y delta, feedback loops and regulators into effectively using the sophisticated diagnostic tools needed to maintain the invisible electrical brains of today's and tomorrow's aircraft? It's a different skill set, demanding both foundational knowledge and adaptability.